All right, so we're running. All right, so periodic table organization. What I like about this unit is it's probably one of the more practical units that we'll do. You know, where it's like, hey, 15 years from now, what will you remember from chemistry class? I would hope it would be like a general appreciation and understanding of how the periodic table works. And so that's what we're going to go over. Like, how do we, beginning, like, what's the history of it? How do we discover it? And then now, like the modern periodic table, how is it organized? And then we're going to talk about electron configuration. So we talked about with the Bohr model, like how you place electrons. I'm going to show you how it actually works. Like, how do electrons actually get placed in the electron, in the atom? Okay, so the periodic table didn't always exist in the form that we have it now. So the grayed out elements, those are like our modern periodic table. But originally, like about the year 1700, these ones in red, these 13 elements, those are the ones that we knew about. You don't have to memorize those. It's just kind of an FYI. Like, that's just, you know, what they were. And we began to discover, like, our rate of discovery, like how quickly we were able to figure these out. It increased as we got better instruments, so we could actually, like, isolate, you know, take a compound and isolate, like, the individual elements more efficiently, a little bit better. And the scientific methods. Scientists got better at being scientists, at, like, designing experiments, preventing, like, human error, like contamination, from preventing them from, like, getting pure lithium or, like, pure other elements. Okay? And so, like, this last bullet point, as we began to discover more elements, the need to, like, come up with a system to organize them came about. Right? Because at first we were like, oh my gosh, that's so cool, we discovered an element. And there wasn't really this thinking of organization, but after a while you get like 50 elements and you're like, hey, what are some like ways we could like find a way to like organize our knowledge of these to make it easier to understand and learn about them and know how to use them to make stuff, or if you know something's made of this, knowing the properties of that certain substance. All right, so the first person that we give credit for like developing kind of like a rough idea of a periodic table was the Russian chemist Dmitry Mendeleev. And this was like his actual periodic table, like right here, which I think is kind of cool. And he organized his periodic table by increasing atomic mass. So that's important. And that's not how we organize our periodic table. Why would organizing the periodic table by atomic mass not be a good idea? Why would that run into some issues? If you remember atomic mass, that is the atomic mass number. That is the number of protons plus the number of neutrons. What would be the issue of organizing a periodic table based on protons and neutrons? Yeah, go for it. Ions, not so much ions, because ions are when you have more or less electrons, and electrons don't have any mass. We wouldn't be so much worried about that. Yeah.
Could they be like the same atomic mass?
Yeah, right. So remember isotopes?
No.
Hey, I thought of something like after the fact. ISO-nu. Isotopes, different neutrons, number of neutrons. ISO-nu. I thought it was cool. Anyways, ISO-nu, because we have isotopes, you could have an element like, say, carbon that is going to have the same number of protons, but they'll have different numbers of neutrons. So what could then happen is you could get a scenario where you could get two elements that have the same mass number, as Kara was saying, right? Same atomic mass. Okay, so that was the downside of trying to organize it by increasing atomic mass. They eventually started to find that you would have elements that would have the same mass number. Okay, so we then were like, okay, so mass number is not a very good way to organize them, and there's something about like more like to the point of like how elements behave. If you organize it by the atomic number, so if you start organizing things by the number of protons, well, if like you look at like lithium, lithium's right here. Lithium has 3 protons. Let me write this one. Lithium has 3 protons. There's no other element that has 3 protons, right? So the number of protons, the atomic number, that's specific and unique to each element. That's why it makes more sense to arrange it that way. Okay? All right, other things. The horizontal columns, we call those groups. These are, I don't know why they didn't just put the arrows here. These are also groups, like all of these. I guess they just got tired of putting arrows. They're like, yeah, I don't know, I'm out. I'm not going to put any more arrows there. But these would also be columns right there. Okay? And then the horizontal rows, so like going left to right, we call those periods. So vertical columns are groups. Here's how you can remember that. In a horror movie, what is the worst thing you can do? Split up. You're stronger in a group. And when you build something, you want to have those like columns, those vertical columns. It makes it stronger. So the groups are the columns, and the periods are just the other thing. I don't know. Okay, cool. Now, this is important for the groups. Similar properties are in the same group. So like, you know, your friend group, you all typically have similar properties, similar features, right? You all like Harry Potter or Pokemon. There you go. So everything in this, and I'm going to go over some of these groups, highlight a few of them, and you'll see that they all share similar features that are in that same group. Okay. All right, moving on. All right, so this is showing that you can divide the periodic table into 3 general categories. Most of the periodic table, and in the leftermost part, everything outlined in black, those are metals. So most of the periodic table are metals. So even things like, somebody was like, wait, sodium, that's a metal? And it's like, yeah. So I'll explain more of like what does it mean to be a metal, non-metal, metal later in the slide deck. But yeah, so most of it left, and then it kind of starts getting into the right part of the periodic table. Those are metals. Then as we go from metals to non-metals, there's a transition period called the metalloids. So the metalloids, they're the blue highlighted part on your periodic table. Now in your notes, you'll want to like, using like a pencil or a pen or something, like kind of like roughly shade in so you can like, because when it's printed out for you, it makes it seem like it can be hard to tell, well, is phosphorus, is that a non-metal or a metalloid? So find some way to make that clear for you. That like, that's the dividing line. Okay? Otherwise, when you look back at this, you'll get yourself confused. Yeah, so then the right to top right part of the periodic table are the nonmetals. So metalloids is the smallest group or category. The nonmetals would be the second smallest, or the middle. Okay. All right, getting into some of the properties. So metals, we say they are solids at room temperature. They're solids at room temperature because swords. Right? Like swords are made of metals and they're solid at room temperature. Otherwise, it's not a very good sword if it's just like liquid at room temperature. Like not going to work, you know? Unless it's a water sword, but that's just weird and not real. Now, when you cut metal, like if you just slice metal like that, you'll get this shiny appearance. We call that high luster or sheen. Or like, you know, like a car, like it'll reflect light. My like family, they built a treehouse, this really cool treehouse in our backyard, and it had this metal roof on it, and our neighbors complained because the light would hit the metal roof and like the luster or the sheen would like reflect into their windows and like blind them. I don't know. I feel like they're being a little over dramatic. I think they're just wanting something to complain about, but you know. Anyways, so we had to like put a layer of paint on it. But point is, metals are shiny. They have a sheen to them. And again, majority of the elements in the periodic table are metals. So when in doubt, it's probably a metal. If you're ever having to like choose between the two of them. And then here are just some pictures of like what these different metals look like. Okay. All right, cool. Some other properties of metals. They can be hammered into a shape, meaning they are malleable. So if somebody is malleable, like what does that mean? Like if I were like, hey, so-and-so so malleable, what are we saying? Sam? Easily manipulated, deceived. That could be like the negative side of it. If I was saying it positively, they're very malleable. Well, how could that be like positive? What was that saying? Yeah, Danielle, go ahead.
Like flexible.
Flexible, yeah, like they can bend easily. So yeah, it could be positive or negative. So metals, you can bend them. Now, like a blacksmith, right? To bend metal, because it's a solid at room temperature, you have to get it to be not room temperature. You got to raise the temperature of it, get it nice and hot, and then you can bang it into a specific shape. You can bang it, into a sword, or other things. Metals are also ductile. Ductile means you can draw it into a wire. So this makes it helpful. Like here's copper wire. This makes it helpful for like electricity. I'm going to show you how metals conduct electricity. Well, because they're ductile, we can make these really long and thin wires that, make it to where you can have like a nice small little tiny wire to conduct that electricity. Okay, moving on. As I mentioned, metals are good conductors of heat and electricity. So there are conductors and insulators. These are opposites of each other. If you're a good conductor, you're a poor insulator. So when I say metals are good conductors, that's the same thing as saying a poor insulator. Now, what is electricity? Like when I say electricity, what even is electricity? You may know? Fundamentally, it is energy, but like, where is that energy coming from? You have a wild idea, right? It's like the wall. It's like, well, yeah, but like all the way down to the atomic level. It's the movement of something. The movement of.
Electric charge.
I think somebody said it.
Electric charge.
What did you say?
Electric charge.
Electric charge called electrons. Yeah, electric charge. Electrons. So negative the electrons. You move the electrons, that's electricity. So a good conductor has a lot of, this says free electrons. So let me compare that to an insulator. So an insulator does not have free electrons. In an insulator, if you have two atoms here, so here's one atom, here's another. When these two atoms come together and they make a bond is where you share electrons. So here they are sharing this pair of electrons. Each red dot is an electron. They do that because by sharing this electron, those two atoms are more stable. So insulators, there's no free electrons. There's no electrons that can move because they're all held up in this bond. Whereas the metals, they're good conductors because when you get a bunch of metal atoms together, they don't share a pair of electrons like the insulators do. They kind of have like a communal set of electrons where it's like this electron, sometimes it belongs to this atom, but then other times it belongs to that metal atom. Or it could move when it's conducting electricity. This electron could move across this entire sample of metal. Okay, so the movement of electrons is electricity, so that's why metals are good conductors. And then heat, why they're good conductors of heat is related to this property. That movement of like that energy throughout the material can then cause your light. That's why your cookware is made of metal. Okay. All right. Cool. Non-metals. Okay. Wait. Yeah, non-metals. So I said that metals are solids at room temperature. So that would suggest that non-metals are not solids at room temperature. Specifically, they are gases at room temperature. So, like a neon sign, neon is a non-metal. It's a gas at room temperature. Oxygen, right? It's a gas at room temperature. Now, if you get metals in their solid state, they usually are brittle. Brittle, you could think of it as like fragile. Think of it like brown sugar. You ever got like a clump of brown sugar, and it's like you go to grab it, and you're like, look at that solid piece, and it just crumbles in your fingers. Like that's what that would be brittle. So sulfur, that would have like a similar consistency there, where that would just crumble. That little clump right there, if you were to grab it, it would just crumble into like the smaller pieces. Same with sand. So yeah, basically they're like their properties are the opposites of metals. Would be a simpler way of saying it. So they're not malleable. You're not making swords or wires out of non-metals. Give you a minute to finish writing the blanks. Okay. So looking at some of the other properties of non-metals. So metals have luster. Non-metals lack luster, or we say they are dull. Right? If you're dull, if I said somebody is dull, they maybe don't have like much personality, maybe kind of boring. Non-metals, they're not shiny. They give off like a sheen. They are poor conductors, meaning they are good insulators. So if you're a poor conductor, that means you are a good insulator. So same picture as for the metals, right? They're good insulators because the non-metals, they hold their electrons really tightly in the bonds between the separate atoms. So they don't move the electricity because electricity is the movement of electrons, and these electrons are held up in the chemical bonds. All right. Moving on. So metalloids. As I mentioned already, the metalloids are this like kind of staircase thing right here. They are a transition. They have properties that are in between metals and non-metals. And by in between, I mean like it depends on the temperature. So on the next slide, I'll show you like if it's a high temperature, they behave like metals. Low temperature, they behave like non-metals. Because they are sort of metals, we call them semi-metals. Yeah, so getting into some of their properties here. At high temperatures, they act like metals. At low temperatures, they act like non-metals. That's why we call them semiconductors. So a conductor, we said metals were conductors, right? They move the electrons, they move that electricity. But sometimes they conduct electricity. Why would that be helpful for electronics? Like, why would then metalloids then, they are the most useful elements to make electronics. Based on those properties, why would that be useful? To be a semiconductor. In other words, why wouldn't you just want to be like a conductor? Like you would think like, oh, we need electricity to run our appliances and stuff, or our laptops. Wouldn't you just want conductors in general? Why would semiconductors be helpful? Yeah, Eliza? Yeah, it's related to that idea. Like you want to have some way of turning it off. So how would Deborah?
So that you can use both metals and non-metals in it.
Say again?
So that you can use both metals and non-metals in it. Like you can use like metals and
So sometimes you want, like, when it's turned on, you want it to behave like a metal. You want it to conduct that electricity, but like, you don't always want your thing turned on. Sometimes you want to turn your laptop off or your phone off. Then you lower the temperature, it then behaves like a non-metal. If you turn it on and you raise the temperature, it starts conducting electricity. It'll then act like a conductor and then run your electronic device. Then you turn it off, temperature goes down, it'll behave like a non-metal. It's really important. That's why it's a semiconductor. Sometimes it conducts, sometimes it doesn't. Anyway, silicone. Ever heard of Silicon Valley? Like in California, they call it Silicon Valley. A lot of like Apple, a lot of like electronic type companies, tech companies are in California. And silicone is the most common metalloid we use in our semiconductors. Technically, you can make electronic devices out of not using silicone. Like you could use, I don't know which of the metalloids are best. I'd heard somewhere that germanium, like it was almost going to be Germanium Valley. Like whenever like they were discovering how to put together these electronics, it was like, should we use silicone or use germanium? I forget why we chose silicone. I think it may have to do with like cost. And the properties of silicone were just a little bit better at modulating that temperature, turning it on and off and stuff. Anyways. All right, getting into like each of the groups. So if we're looking at the very first group here, group 1, we call those the alkali metals. Okay, so this very first group, so lithium all the way down to francium. And I want you to know that they are very reactive. So next class, you're going to get to do a lab where you're going to get to work with a bunch of different elements, a bunch of different metals, and you're going to put hydrochloric acid on them, and you're going to see how violently they react to that acid. It's actually kind of fun. But they're really reactive. Now, the reason why they're reactive, if I draw the Bohr model of lithium. So here's lithium. Lithium has 3 electrons. I'll draw those electrons. Let's do orange. Halloween. I'm actually not going to do that. I'm getting black all over my orange marker. Okay, 3 electrons. Now, the outside electron, these outermost electrons, those are the valence electrons. So they all have 1 valence electron. If you were to draw the Bohr model of all these other atoms in this group, they would end up with 1 electron in their outermost shell. Now, they form +1 cations. You're like, how does that work? Well, if you lose this 1 electron, you lose an electron, you would then be +1. Because each electron is -1, so you lose 1, you would be +1. Now, why would lithium want to lose that electron? Anybody know? Why would elements want to lose that electron? Well, in other words, what would happen if I get rid of this electron? And why might that be beneficial? Think of a seesaw. What happens in a seesaw if there's like an open seat? It's not balanced, right? It's off balance. So elements are the most stable when they have a full outside or valence shell of electrons. So if I'm lithium, if I get rid of that electron, now it would have 2 electrons in that first energy level. It would have a full first energy level. Okay, that's why it wants to lose 1 electron and be a +1 cation. So 1 valence electron +1 cation, those are connected to each other. And because it only needs to lose 1 electron, it's really reactive. It's really motivated to get rid of that electron. That's why it's reactive. All right, moving on to group 2. So if you go to one of the groups or columns just to the right of group 1, you get group 2, and we call those the alkaline earth metals. Now here's how you can remember, because it's like, well, you have the alkaline metals and then the alkaline earth metals. And it's like real creative scientists. Like how am I supposed to remember that? Well, group 2, there is 2 words in alkaline earth metals. Right? Whereas alkaline metals, group 1 is just 1 word. Okay. We all get it. Now, I really want you to key in on that. They have 2 valence electrons. They are really reactive, and they form +2 cations. Those are the most important properties here. Now, and then understanding why they form +2 cations and why they're so reactive. It goes back to the Bohr model. If I draw the Bohr model of beryllium, so beryllium has 4 electrons. 2 can go in that first energy level, and then 2 can go in that second energy level. So it's the same story as what you saw with the alkali metals, group 1. If we lose these outer 2 electrons, it wants to do that. It wants to get rid of those 2 electrons so it could then have a full first energy level. If I lose 2 electrons, that makes you a +2 cation, because each electron is -1. Okay? That's why they're reactive. They're really motivated to lose those 2 electrons. Now, these aren't as reactive as group 1, just because it's harder to lose 2 electrons versus 1, but they're still motivated to do that. Okay? Okay. Moving on to the transition metals. So, the transition metals are groups 3 through 12. Basically, it's the valley. Meaning, this is group 3 right here. This would be like group 3, and then this is group 12. And remember, the groups extend all the way down. So it's this whole rectangle here. And I say valley because it's like you're higher up here, then it dips down, and then it goes back up. 3 through 12, that whole thing are the transition metals. The physics people do it, like having a party in the hallway. Okay, anyways, they are less reactive than other metals. That's the most important thing for right now to know about the transition metals. Not as reactive. When we get into electron configuration later in Unit 3, I'll explain that these have like some unique ways that they organize their electrons and like the shape of the atom. But for right now, they're just less reactive than the other elements. Other metals, excuse me. Okay, then getting into the inner transition elements. So where this came from is here. These right here, the inner transition elements, these could squeeze in right here. So this slide, this table here, is this right here. It's the bottom part of the periodic table. Now, why would I not want these to be put right there? Like, what's the benefit of pulling these out and then pasting them down here? Why not just like add them in here and just make it all one table? Save space. Yeah, think of how wide this would be. Like twice as wide if you tried to squeeze this into this actual row here. And what I mean by squeeze in, like this is 56, this is 72 right here. So these are 57, and then this ends at 71. Like that would squeeze in right there. And then this is 88. This is 104. So this is 89, and then this is 103. That's what I mean, they squeeze in right there. But to save space, we pull them out, and we chose to pull these ones out because they have similar properties. It's not just like arbitrary, like they just had similar properties right here. Okay. All right, so showing you the actual notes for that slide. Collectively, these two rows here, we call them the inner transition elements, where the first row is called the lanthanoids. Another name for lanthanoids, so on that formative, you'll also hear it called the lanthanide series. I added these notes in, so you'll want to add these on your slides. The lanthanoids are also the lanthanide series. They're just synonyms. You'll hear it both ways. Actinoids is also called the actinide series. That's this right here. This bullet point and this bullet point, I added a lot of editing on this slide. I'm sorry. The lanthanoids are the rare earth metals. Okay? Lanthanoids are the rare earth metals. Actinoids, you see radioactive. The actinoids, this group right here, actinoids, or the actinide series, all of these are radioactive. Some of the lanthanoids are also radioactive, but not all of them. But the lanthanoids, these are the rare earth metals. How about this? Lanthanoids, LA. You know how rare it is to own a home in LA, given how expensive it is, or how rare it is to drive without running into traffic in LA. So lanthanoids, the rare earth metals. Oh. All right, moving on. Group 7 are called the halogens. So in pink here, here's the halogens. Now, you're like, group 7, where did they get that from? Well, they also are called group 17. So the 17 is if you go 1, 2, 3, 13, 17. If you count all of the columns, all of the groups, you get to 17. Now, let's say you skip counting, you don't count the transition elements, and you go 1, 2, 3, that would then become 7. See that? So that group 7 or group 17. So just depending on if you include or don't include the transition elements. Bless you. All right, so the halogens, we say they are highly reactive. Now, they are highly reactive because they need one more electron. So they're actually the opposites of the alkali metals. So if I draw fluorine, the Bohr model of fluorine, fluorine has 9 electrons. So 2 electrons can go in that first energy level. And then remember, the second energy level can hold up to 8 electrons. But fluorine, it only has 7 that are in that outside shell. Yeah. You got it. Yeah, good, Eliza. Yeah. So check this out here. Fluorine, for fluorine to be the most stable, it wants to get one more electron, then it would have a full 8 electrons in its second shell. And I told you, and as Eliza said, everything in group 1 here, they want to lose 1 electron. So it's like Match.com, right? A match made in heaven, right? These metals, they give their 1 electron to the halogens. That's why NaCl, what's NaCl? What's this?
Salt.
Salty Bay, right? The salty. Okay. NaCl, that's why those go together, because sodium wants to get rid of 1 electron, chlorine wants to gain 1 electron. It's really that simple. Like it's kind of beautifully simple how this all works. And that's a common thing. So Li and Cl, they'll want to pair up, and so on. Anyways, if these halogens gain 1 more electron than they normally would have, that's why they form -1 anions. Now, related to this idea is that the fact that they exist diatomically. Di means 2. So fluorine always wants to exist in nature paired up with another fluorine. Or hydrogen always wants to pair up with another hydrogen. Why would that make sense? Given what I showed you with the Bohr model, why would they want to exist diatomically? Why would fluorine want to have a buddy with it? What would that allow them? Yeah.
Lose electrons?
To do it?
Lose electrons?
They wouldn't lose electrons, but you're on the right idea. They wouldn't lose share. Yeah, good. So if I draw the Bohr model of a second fluorine, so this is another fluorine, then this fluorine also has 7 valence electrons, and it's like, oh my gosh, I need 1 more valence electron. And so they're like, hey, what if we just like share a pair together, and then they'd be stable. That's why they're diatomically together.
So they both can have 8.
They both, yeah, by sharing 1 electron, they then would have 8. Yeah. Anyways, cool. All right. Anyways, going to group. This one has 3 names, 4 names really. The noble gases, aka group 0, aka group 8, aka group 18. So the reason why they're called group 18 is because if you go 1, 2, and you include the transition metals, so 3 count the columns of the transition metals, 3, you would get to 18. But say you're like, who cares about the transition metals? They're weird. You go 1, 2, skip the transition metals, and you count 3 here, then you would get to 8. Now, they're also called group 0. They're called group 0 because if I draw the Bohr model of, say, let's do neon. Neon has 10 electrons. 2 go in the first shell, and then 8 can go in the second shell. Why is that a big deal that 8 can go in the second shell?
Because they have like full electrons and atoms.
Yeah, good. Then you would have a full second shell. Then it would be stable. So why these are, we say inert, they are not reactive, is because neon is a strong independent atom. It doesn't need any electrons. It's all stable here. It doesn't want to pair up with another atom. It doesn't need to share any electrons. It's already stable. Okay? On the formative, one of the questions says like, naturally they don't pair up or something with other elements, meaning like you would have to like in a lab force them to try and somehow pair up with something. Like it doesn't, naturally they just want to be all by themselves. Okay, cool. That's it. We finished it. Let me show you on the formative, just some like, make sure we're all on the same page. I didn't put a number on this question, the representative elements. I forgot to include those in your notes. People don't usually talk about them. The representative elements is basically referring to everything on the periodic table but the transition metals. So basically you just don't have to do that question. There's not like a little marker on your formative to have you do that question. Okay? So I think it was question like 4 or something. It would go with this one. Okay? All right, so that's that one. And then the second part of the worksheet, the answers to these blanks, use the answers from this answer bank, where you're only going to use only once, right? Use each word only one time for these blanks. And then you're not doing this question. So the blank for 24, that's referring to this right here. I'm not saying that's the answer to that. Like that's not, the answer isn't 24. That just that little tick mark on the formative, the 24 is referring to this. Okay. Let me know if you have questions.